This lesson is on confidence intervals for one proportion. The goal of statistics in general is to take a small sample and to make a larger conclusion about a population. So a couple of term words to get us going here. Statistic, this is a word that describes a sample. I remember this with S for S there. A couple of examples of statistics. X bar, this is a symbol for a sample average. I have S, that's the symbol for a standard deviation. I have P hat, this is for a sample probability. P hat. And this is for percents or for proportions or for probabilities. So any of these three things, these are all different terms, symbols used when describing small groups of individuals, samples. If I'm trying to describe a larger, more encompassing thing, a population, I use something called a parameter. P for P helps me to remember that. I'm going to match up and I'm still going to look at average, standard deviation, and percentages here, or probabilities. The symbol for a population average is mu. The symbol for a population standard deviation is sigma, kind of looks like Charlie Brown with a little whoosh for the hair there. And the symbol for a population probability is P. So again, the goal of statistics is to take a small sample and make a conclusion about a population. So I'm going to be using these statistics to try to make conclusions or inferences about parameters. We're going to assume that we're starting with some sort of a population model here today. I'm going to be working with a normal distribution. And because this is a population model, when I'm describing the center or the average, I'm going to go back up here, population average. I'm going to be using the symbol mu for the center. I'm going to mark it right there on the center of my curve. The normal model is sometimes called the bell curve because if you look at this, it kind of looks like a bell. If I'm talking about spread, that's how far up and down this curve changes. That's the standard deviation, and that was that symbol sigma. So this means if I'm going in this direction on the curve, I'm adding sigma. If I'm going in this direction, I'm subtracting sigma. So this is 1, 2 tick marks away, 2 sigma away. 1, 2, 2 sigma away from the center in the other direction. And as you can see, this average and the sigma sort of uniquely determines how I'm drawing out this picture. It tells me where to start and it tells me where to count. So the notation I use here, X, this is just the name of the distribution. This could be like cats or number of candies or literally whatever you're looking at for that model. Capital N, that stands for the normal distribution. It says it looks like this curve here. This first number that I'm writing down, that's my average. That's the center of my curve. And the second number that I write down is what I count by, my standard deviation. And the nice thing about the normal distribution is that it follows really strict area rules. One of those strict area rules is called the empirical rule or the 68, 95, 99.7 rule. Here's how this works. I'm just going to write it down briefly and then we'll look at some examples. If I am within one standard deviation, one SD, of the average, I have 68% of my data. If I am within 2 standard deviations of that center, I have about 95% of my area. And if I'm within 3 standard deviations of the center, I have about 99.7% of the area. So as you can see, even on this curve up here, I have a lot of area within 1 standard deviation up and down. The 68% lives here. 2 standard deviations. I would say 2 standard deviations away from the center is usual. It's usual because I'm in here 95% of the time. I'm going to remember that 95% for later. 3 tick marks away. It's not the whole curve. You can see how the curve keeps going on forever there, but 3 tick marks away, there's really not that much left at that point. So if I go all the way out here, I'm in the boons, and I'm looking at 99.7% of the area. I'm going to look at the next page, and we're going to look at some applications of this thing, just a couple quick problems. So first problem on this next page, and I'm going to come back to the 68, 95, 99.7 rule. It says, suppose that X, that's a distribution, is normally distributed. So I'm going to already start to draw this. This is saying this thing looks like that bell curve. With a first number reminder, this is my average or my mu, average 25, and a standard deviation of 5. So I'm going to draw that on my curve. My center is 25, and I'm counting by 5. So going in this direction, I have 30, 35, 2 standard deviations, that's pretty far out. 40, that's 3 tick marks away, 1, 2, 3 standard deviations, I'm in the boons. Other direction, 20, 15, and 3 standard deviations away, 10. For this problem, it wants to know how much area is within 10 and 40. Well, 10 was 1, 2, 3 standard deviations down, and 40 was 1, 2, 3 standard deviations up. So I am within 3 standard deviations of the center. And thinking back to the rule I had earlier, the 68, 95, 99.7 rule, if I'm 1, 2, 3 standard deviations away, I must be looking at about 99.7%. I've written that as a decimal, 0.997. I'm going to do another one. I'm going to find the area between negative 17 and 11 for this curve. I'm going to draw the curve. I'm not great at drawing these things. You're probably a better drawer than me at them. Just do your best. X says I have some sort of a curve, could look like anything. This says normal curve, can't look anything like anything now. It has to look like this sort of bell. Negative 3 is the center. I'm putting that in the center just right there. This is my standard deviation. I'm going to add and subtract 7. I'm careful with my numbers. I'm starting with a negative here. Negative 3 plus 7 yields 4. 4 plus 7 yields 11. I'm going to go in the opposite direction here. If I'm 3 down and I take away 7 more, I am 10 in the hole. That's negative 10. Negative 10, take away 7 more. That puts me at negative 17. My numbers here, I lucked out again. Negative 17 to 11. I am within 2 standard deviations. This should be symmetric. This is what I meant by I'm not the best drawer at these things, but we do our best. If I'm within 2 standard deviations of the center, then I am at the 95 part of the 68, 95, 99.7 rule. So the percentage or the probability of having a value between negative 17 and 11 is 0.95. Now, things get a little bit messier if I have something like this. Notice this isn't a 2-number problem. Like these both had 2 numbers, a low and a high. This just has 1 number. The other issue here is if I look at the same curve, I'm just going to draw out a quick sketch of this thing. Negative 3, 4, 11, and here's my number 10. It doesn't line up perfectly with this 1 or 2 tick mark away. In fact, it's not a clean number of standard deviations that I can visually see that easily. So I might have to come up with a new technique for dealing with these problems where it doesn't line up perfectly. So I'm looking at 10 or less. This is going to be shaded to the left. When I'm in a situation like this, I use something called a normal table. So here's going to be my process. First step, I'm going to calculate a z-score to figure out exactly how many tick marks away. And already as a guess, I see that z is about, well, it's more than 1 tick mark, but it's less than 2. So I might guess that my z-score here is going to be 1 point-ish. Ish isn't a very good guess. We'll have to do better than that. We'll see what we can do. The way that I'm thinking I'm going to find this z-score, and I'm going to do it for this particular problem here with numbers, but then I'm going to come up with a formula here on the side. First thing I want to know is how far is 10 away from the -3? Well, if I go 10, take away -3, minus negative is going to make this a plus. This tells me that 10 is 13 units away. I'm 13 away, but I need to know what I'm counting by. If I was counting by 13, I'd be exactly 1 standard deviation away. If I was counting by like 6.5, I'd be exactly 2 standard deviations away. But I'm not counting by 6.5, I'm not counting by 13. I'm going to divide this by the thing that I count by. I'm counting by 7. So in my calculator, I'm going to do 13. This is the total gap. And I'm going to divide this by the thing I am counting by, the standard deviation. So I'm going to divide this by 7. I'm going to type that into my calculator. I have 13 divided by 7. And when I hit enter, I get, it looks like 1.86. This is great news. It's more than 1 tick mark away and it's less than 2. 10 is way closer to 11 than it is to 4, so I'd expect it to be closer to 2 than 1 standard deviation away. So 1.86 seems pretty reasonable. I'm going to write down the formula for what we did here, and I'm going to ask that you sort of put a star next to this thing. It's important. It's going to show up a lot when you're working with the normal distribution because everything is based off of where it is on the curve. The z-score tells us where it is on the curve. So to find the z-score, I take the value that I care about, I subtract the average or the center. I'm going to informally just call this thing center, and I'm going to divide it by the standard deviation. Again, you should think of this as being the number of tick marks from the middle, or from the center. And if we had something like a normal table, we could look these tick marks up. Let's see what that looks like. So I'm going to go through this nice 3-step process here. My first step, I'm going to draw a picture. My second step, I'm going to calculate the z-score. That's how many tick marks away I am. And third step, I'm going to look those z-scores up using a normal table. So here I go. First step, I'm drawing the curve to the best of my ability. Center, I'm still working with that -3,7 model. We'll switch it up here in a bit. Counting by 7, still 4, still 11 here. My value is 10. It didn't line up perfectly. A little bit of panic. I couldn't use that 68, 95, 99.7. That's okay. I don't have to be able to use it. And I'm shading to the left. Second step, I'm going to find the z-score. I find the z-score by taking my value, subtract the center, and I divide the standard deviation. I'm going to start with that value. The value I care about in this problem is 10. I'm going to subtract the center. The center is -3. And I'm going to divide what I'm counting by. I'm counting by 7. I'm going to round all of my z-scores to 2 decimal place. That's to the hundredths place. We'll see why in just a second. When I type this into a calculator, I get 1.86. And my next step, I'm going to go to my notes here. I'm going to grab a normal table. We're going to look this thing up. Okay, I've got this beautiful normal table here. Let me point out what's going on. My first two digits of the z-score show up here. My last digit of my z-score shows up here. If you look at the picture, you'll notice that it's shaded to the left. Whenever you're looking for an area shaded to the left, you are going to take the value inside of the table. I'm going to break this up for this z-score, and we're going to see that this is a grid. I'm going to see where these things meet. Wherever they meet is going to give me my probability. Okay, my z-score here, 1.8. So the first two digits, this tells me which row I'm going to be in. I'm going to go to the table. I'm just going to highlight it here. I'm in the 1.8 row. My next digit, this tells me the column. I'm going to be in the 6th column. So I see that here already, 6th column. And now I'm going to look at my grid, and I'm going to try to find where the 1.8 row meets that 6th column. So 1.8 meets the 6. This is a good time to kind of pull out a straight edge to try to see these lines a little bit clearer. As you practice this more, you'll get pretty fast at it. I'm seeing that I get an area of 96.86, assuming that's the area shaded to the left. So my value in the table is 96.86. I'm looking up at the top picture here. It's shaded to the left. That's what I want. This tells me the likelihood of 10 or less is 96.86%. So this is a nice starting place, and I like looking at this normal distribution to begin the term with one of these population models, because this will end up being the core for making a ton of predictions when it comes to statistics. I'll be able to use a normal distribution to guess what's happening for a population success rate, comparing two different population probabilities, and looking at population averages. I'm going to look at another one of these problems with you. We're going to move to page 3 of this packet that I have printed. Okay, fresh problem. It says the number of hours of sleep an average person in the US gets. It's normally distributed, and I have X, so this is my distribution, tells me to start drawing a curve. N says I'm going to draw that curve like a bell or a hat. First number 8, that's the average of my distribution. I'm putting an 8 there. And my standard deviation is 0.5. So I'm going to count by 0.5. So that's 8.5, that's 9, that's 9.5. And for this problem, I'm looking at an area between 9.25 and less. So I'm going to mark 9.25 on my curve. That's right here. Or less, I'm going to shade that to the left. Going through my process, I've drawn my picture. Next step, I'm going to find my z-score. Z-score is value. That's my value right there. Minus the center divided by the standard deviation. So in this case, the value that I care about, 9.25. The center of my curve is 8. And my standard deviation is 0.5. I'm going to type this into a calculator and see what we get. But before I type this in, I'm just going to look at my picture to see if I can come up with a guess for it. 9.25 is here. This looks like it's 1, 2, in between 2 and 3 tick marks away. In fact, it looks like it's perfectly in the middle of those 2 tick marks. So my guess is that this is going to be a z-score of 2.5 or so. I'm going to type this in just to be sure. And when you type this in, you might want to type in the top on its own, 9.25 minus 8, and then divide that by 0.5 as a second step. When I do this, I get 2.50. That's my first step. Now for my second step, I'm going to pull out that normal distribution table again. This starts 2.5, that's the row, and it ends with 0, that's the column. So I'm pulling out my table. 2.5, that's my row. 0, that's my column. And these look like they meet up right here at a table value of 0.9938. So if my picture is shaded to the left, I'm good to go. If it was shaded to the right, I'd have to get clever somehow. I kind of lucked out on this one because, again, this is another one that's shaded to the left. So the probability that it's less than 9.25 is equal to 99.38. So interpreting that, this means there's a 99.38% chance that someone gets 9.25 hours of sleep each night or less. That's most people. That's almost 100% of people get 9.25 hours of sleep or less. I'm looking at like 0.0061 or 0.61% of people that get more than 9.25 hours of sleep. I'll show you how I came up with that 0.62% here when we're looking at this next problem. I want to find the probability of all people that get more than 7 hours of sleep. Same steps. I'm drawing my picture. I'm finding my z-score. And I'm going to look the thing up in a table. I still have 8 as my center. I'm still counting by 0.5, so here's 8.5, here's 7.5 and 7. And I keep counting until I go past my value. My value is 7. I kind of luck out because this is perfectly on one of those tick marks. Do you see how this is 2 standard deviations down? I'm going to expect when I do this formula to get a negative, it's down from the center, 2, it's 2 tick marks away. Let's use the formula of a z-score. I have my value is 7, minus the center, my center is still 8, divided by my standard deviation, I'm still counting by 0.5. I type this into a calculator, and I get a z-score of negative 2.00. I'm still writing it with 2 decimal places, but look, 2 tick marks down, just like I thought. This says more than 7, so I'm going to be shading in the direction where I have numbers that are larger than 7, for example, direction of 8 there. And I'm going to look up this negative 2.0 row meets the 0 column. I start out on this side, I'm seeing nothing but positives, so I'm going to have to flip that over so I can see those negative z-scores. Negative, this is looking much better. 2.0 meets the 0. When I do this, this gives me 0.0228. I'm going to write that down. The table value was 0.0228. The problem is when I'm looking at my picture, this doesn't look like it's 2% that's shaded in. This looks more like it's like 97 or almost 98% shaded in. And that's because the table value is always giving me the area to the left. So this tells me that this little tail to the left is 0.0228. If the entire curve is 100%, then if I want the area to the right, that's the opposite or the complement of the area to the left. So whenever it's shaded to the right, I'm going to have to go from 100%, the whole curve is 100%, and I'm going to subtract this tail to the left that I don't want. In other words, whenever it's shaded to the right, I do 1 minus the value from the table. In this case, when I do 1 minus the table, I get 0.9772. So in other words, the likelihood that someone gets 7 or more hours of sleep is 97.72%. Let's look at another one. We've done one now where it's shaded to the left. We've done one where it's shaded to the right. This will be the final one that we do together for just reviewing this normal distribution, and then I'm going to put it into practice. We're going to look between two values, between the values of 7 and 9.25. Still the same process. I like to think that I'm getting better at drawing these things each time I draw them, but I'm not convinced that's true. I'm going to start with my center. My center is 8. I'm still counting by 0.5. So I have 8.5, 9, 9.5. On the other side, I have 7.5 and 7. Unlike that last problem, the problem before where I only had one value at a time, for this one I have two values that I'm working with. I have both 7 and I have this value up here at 9.25. And I'm going to be shaded between these two numbers here. So I'm going to shade between the 7 and the 9.25. I think you might see Fiona here in the background. Hey, Fiona. When I have two values, I'm going to calculate two z-scores. I'll have a large z-score and a small z-score. To find this large z-score, I'm just going to take the large value, and I'm going to go through the process. So I have 9.25, my large value, minus the center, 8. And I'm going to divide by that standard deviation of 0.5. When I do this again, I can see this looks like it's 1, 2, 2.5 tick marks away, 2.50. I'm going to do the same thing for the small one. The small one is 1, 2 tick marks down. So I have 7 minus 8 divided by 0.5. I have negative 2.00. My next step, I'm going to look both of these things up in the table. But if you look at these values, 2.5 and negative 2, if these seem familiar, it's because it's the same values that we were just working with. So I'm going to cheat a little bit. I'm going to use the same table values I had before. One of my table values, when I looked up that larger z-score, was 0.9938. I'm going to put that on the picture so we can see what's going on. That means when I'm looking at this 9.25 and down, this includes all of my area that I want, but also this little tail that I don't want. This total thing here is 99.38%. What I want to do is I just want to get rid of this part that I've overshaded. When I look up the smaller z-score, table value there is 0.0228. That's exactly the amount I'm overcounting by. That's this little tail here. So if I want the area in the center, I'm going to take this amount that overcounts it, and I'm going to subtract this little tail here that I don't want. In other words, whenever it's between two values and I want that area, I'm going to take the large table value and I'm going to subtract from it the small table value. So in this case, I have 0.9938 large table value minus the small table value 0.0228. When I do this calculation in my calculator, I get 0.9710. So in other words, if I'm wondering what percentage of people get between 7 and 9.25 hours of sleep each night, That's 97.1% of the population. Okay, again, if it's shaded to the left, I'm using the table value. If it's shaded to the right, I do 1 minus the table value. And if it's between two numbers, I'm going to take the large table value, take away the small table value. If you're following along as one continuous video, this might be a good spot to take a break, get a drink of water, and come back. I'm going to keep going here, but let's see what we can do. I mentioned a moment ago that this was a model that showed up a lot and would help me make predictions. In Normal Stats 1 course, you learn about 3 distinct models that show up a ton. One of these models, this is called the central limit theorem. I abbreviate it as CLT, like a delicious math sandwich, is that averages follow a normal distribution with the center of mu. Sample averages should look like my population average. This is my statistic symbol again. This is my parameter symbol again. And a standard deviation of sigma divided by the square root of n. If I'm trying to do a problem about averages, if I'm trying to do a problem about totals, this is usually the model that I work with. X, if I'm looking at counts, so this is for the number of successes, has an average or a center of n times p. N is the number of trials, p is my probability of success. And a standard deviation of square root of n, number of trials, p, success rate, and q, my failure rate. I use this when I'm working with counts. And last model that we'll be working with, and I'm going to be using this one a lot today, is my sampling model for my sample proportions. It says my sample success rate should look like my population success rate. I'm going to give you an example of that already. If I flipped a fair coin 200 times, I would expect for my sample that I should get close to 50% the population success rate. Now, if I always got 50% for my sample, that's like Stepford wife kind of weird number, right? That'd be weird to always get exactly 50%. Sometimes I might have 48, sometimes I might have 53. So my success rate will vary by the standard deviation. And that standard deviation is square root of PQ over my n. I'm going to use this model when I'm dealing with percentages. Just to note, I can actually do either one of these things. They're fairly interchangeable because I can change a count, say 10 successes out of 20 trials, into a percentage by doing the 10 divided by the 20, and vice versa. We're going to be working way more with percentages though, so it's going to be easier for me to use the second model. I'm going to rewrite this model again. Throughout the term, when I'm checking assumptions, we'll see that there are often 3 of them. The first assumption will do with a sample being random. When I say something is random, I don't mean you're using a random number generator. I'm really just concerned that the sample was collected in a way where there's no bias. My second assumption check is independence. Independence means that one person or one sample does not affect another sample. Sometimes it's really hard to judge if something affects another person. There's a backup for this. If I sample less than 10% of the population, I can assume things are independent. For example, if I eat a Skittle, a red Skittle, I've lowered the number of Skittles in the world, but not by that much because I've only removed one out of like billions and billions of Skittles. Now, if on my desk I only had 5 Skittles and you ate one of my 5 Skittles, I'm going to notice that. That's a substantial proportion of that. I say I notice things when it happens more than 10%. Finally, large N. Large N in this case means I want to have 10 successes. Successes is N times my P. And I also want to have at least 10 failures. That's N times my success letter is P, my failure letter is Q. I want to show you an example of this. We are told that a coin is fair. I'm going to label things already. If a coin is fair, then I should, for the population, have a success rate of 50%. That's what it means for a coin to be fair. I get heads 50% of the time. That also means I should get failures or tails 50% of the time. P and Q are complements. They add up to 100. If this was 70, this would be 30. They're opposites. With 68% certainty, I'm seeing that 68 and that's reminding me of something. Remember, within one standard deviation was 68% of my area, 2 standard deviations was 95, 3 standard deviations was 99.7%. So this is saying with 68% certainty, within 1 standard deviation of the center, what proportion or how often should you get heads in 100 flips there? Proportion. So for my models, I'm not dealing with averages, I'm not dealing with counts, I'm asked something about percentages. So my model is P hat is normally distributed with the center of P and a standard deviation of root PQ over N. I'm going to plug in what we have. P hat is the name of the model. I actually never plug anything in for this. It just reminds me that I'm looking at percentages for a sample. I do plug in 0.5 here for P. That's the center of my model when I'm drawing my picture. And as a separate thing that I'll type in my calculator, I have the square root of my P, 0.5, my Q, 0.5 again, and my N, 100. I'm going to type the square root into my calculator here real quick. My center is 0.5. If you want to write another digit and think of that as being 50%, it is 50%. That's my success rate for heads. Great. And when I type in this standard deviation, I get 0.05. Let me draw out that picture and then let's put everything together. This model tells me that I expect my success rates to follow a curve like this. And what do I think the most likely success rate is for a coin flip? Well, I think the most likely success rate for 100 coin flips is 50%. Again, this is going to vary, but the amount it varies by is going to be 5%. So this would be 55 here. This would be 45 here. I'm adding and subtracting 5%. I'm going to draw another standard deviation out 2 tick marks away. That's 60 here. Another tick mark away here. That's 40. So if someone wanted to know what should happen 68% of the time when I flip a coin, well, I'm remembering that that's 1 standard deviation or 1 tick mark away from the center. So I'm going up and down 1 tick mark. This center area is what should happen 68% of the time. So in other words, I expect, and when I say expect, I mean 68% of the time. I'm not entirely confident with this thing. I wouldn't bet on this. I'm not like 99% sure, but I expect 68% of the time I get a sample success rate P hat between, on the low end, 45%, and on the high end, 55%. Kicking this up just one more notch. Same thing for a coin flip. Now, if I wanted to be more certain or more confident, I'm going to have to guess more values. So 68% of my curve was here. 95, this was within 2 of those tick marks of the center. So I go 1, 2 tick marks down. I'm glad I labeled this thing down 2 tick marks. Makes that easier for me now. And 2 tick marks up. Looks like the curve has crazy hair or something. I'm looking at the area between these values here. That's 95%. I'm seeing that's a low value of 40 and a high value of 60. Now, as these get more complicated, it might help to kind of have a formula for what I'm working with. So notice really what's going on here. I started at my center, and I'm going to go up, add to go in this direction, and subtract, I subtract to go down in this direction, 2 of those standard deviation things that I'm counting by. I found the center by that symbol P, and in our case, P was 50%. I went up and down 2 tick marks, and I found that standard deviation by taking the square root of my P times my Q, dividing it by my N. When I did it for these numbers earlier, that was my 0.05 number. So when I simplify the math, I have 0.50 plus or minus 2 times 5% is 10%. So I have 50, give or take 10. 50 take the 10 or 50 take away 10 gives me a low value of 40. 50 give or add the 10 gives me a high value of 60. So I would say I am 95% certain that I have a success rate between 40% and 60%. I'm feeling a lot better about those odds. Those feel like good gambling odds at this point. Not that I would recommend that, but I am 95% sure that if you flipped a coin 100 times, you would get heads between 40 and 60% of the time. If some of you are more risk adverse and you wanted to be 99.7% sure, you might want to think about going even further out on your curve. In fact, in a lot of ways, it's this number here that determines how confident you are. This value is called a critical value. It determines your level of confidence. Let's look at what that looks like here. So I've rewritten this interval as P plus or minus this Z star. This was my, if I was dealing with 68%, then I went up and down. The star means up and down, 1 standard deviation. If I wanted to be 95% sure, this amount that I was adding and subtracting, this critical value, was 2. And I'll say 2-ish. We'll have something more precise later. And if I wanted to be 99.7% sure, I go up and down 3 tick marks. So this Z star symbol that I'm using, this is my critical value. It tells me the number of standard deviations that I need to add and subtract to get a certain level of confidence. This interval tells me what I should expect for P hat based off of the population value P. Now I want to show you something kind of cool here. This interval does the complete opposite of what I want to do. In stats, I want to start with the sample, P hat, and figure out what should happen for a population P. I want to go in the other direction. To do that, all I'm going to do is take this interval, P plus or minus Z star, my critical value, square root PQ over N, and I'm going to change the symbol. So instead of going from P hat, from P to P, sorry about that. I'm thinking ahead. That's what happens when you think too fast. I want to go from P hat to P. So I'm going to switch my hats. Instead of the symbol with P, I'm going to put in P hat. Instead of a symbol with P hat, I'm going to put in a symbol with P. I'm just rewriting the names of things. So my new center is going to be P hat, my sample success rate, plus or minus Z star square root P hat Q hat over N. This now gives me an interval of what to expect for my population success rate P based off of my sample. And this was a huge, huge accomplishment in 243. This allowed me to make large populations based off of the small sample. As with any stats thing, those 3 assumptions are showing up. Random, that's telling me that there's no bias in my sample. Independence, I'm hoping that one thing doesn't affect another, or that I'm sampling less than 10% of the population. And large N, Large N means that I want at least 10 successes and 10 failures. Previously, this was expected number of successes and failures. Now I'm dealing with the real thing. These are successes and failures that I can count. Example 9 involves doing an in-class survey. So I'm going to skip that one, and I'm just going to do example 8 here. Using a random sample, an employee at the PCC bookstore finds that 97 out of 112 customers use their credit card to pay for books. Create a 95% confidence interval for what should go on for all PCC students. Let's list what we know. I start with my success rate. I had 97 successes and 112 trials. I don't know what that number is, so I'm pulling out my calculator here to type that in. I got 86.61, 0.8661 or so. You can leave it as a fraction if you want to be a little bit more accurate. I might leave mine as a fraction. This tells me that my failure, if I had 97 successes out of 112, then everything left over, 15, 112 take away 97 is 15, things are failures. 86% of the time there's a success, so that means that 13.39% of the time there's a failure. They don't use a credit card. This was for 112 samples. I only need one more number and then I'm in the clear for just plugging things into this formula here. My final number is my critical value, C star, and in this case, it's approximately 2. Why 2? I want to be 95% sure, so I'm on the 68-95 part of that 68-95-99.7 rule. I'm 2 tick marks away. Putting the thing together in an interval, I have my center, so I guess that about 86% of PCC employees or people at the bookstore use their credit cards to pay for books there. I want to be 95% sure, so I'm going to go 2 standard deviations away, or standard deviation like things. We'll see that this has a slightly different name. And my standard deviation like thing is square root of PQ over N, except it's with samples, P hat, Q hat over N. My success rate, 86.61%. My failure rate, 13.39%, and this is out of 112 samples. I'm going to type this into my calculator and I'm going to see what I get. I tend to write my final answers 3 decimal places. You can use more if you would like, but I think minimum 3 is probably a good idea. I have 0.802 for the low. And on the high end, I have 0.930. I'm going to write this out as a sentence. I would say we did the problem together. We are 95% confident that the interval of 80.2% to 93.0% contains the percent, the true percent, the population percent of all PCC students that use their credit card to pay for books at the bookstore. This is a conclusion about all PCC students, like 27,000 PCC students. And I came up with that conclusion using only 112 individuals. That's the incredible power of statistics. This is with a relatively small sample size. I can figure out what's going on with very, very large populations with a certain level of accuracy. I'm not going to be right all the time, but I actually know not only what my guess is, but how often I'm going to be right in this guess. I am 95% sure that I'm going to see something like this. I only anticipate something outside of this, maybe 5% of the time. I'm willing to take those odds. If you wanted to be more sure, if you want to be 99.7% sure instead, just change this to a 3. Easy fix, you're even more confident. The downside, your intervals get bigger, you're guessing more values. So your level of accuracy and your precision kind of go against one another there. If you want to be more precise, a smaller interval, you need to be less accurate, less confident. I'm going to hit you with a whole bunch of vocab here. I'm going to highlight this thing, but I'm hoping for the most part this is mostly review stuff and that you've seen this material in a 243 class. This is really intended to be just a refresher for now. Writing out my interval, p hat plus or minus z star, square root p hat q hat over n. Okay, labeling things. P hat. This was my center. This was my guess for what's going on. I call this my best point estimate. So for example, in that last problem, I guessed that 86% of students use their credit cards to pay for books. This z star, I'm still calling this thing my critical value. This thing that I used to call the standard deviation and now has a new name, this is called the standard error. It's the standard error when it's based off of a sample. It's a standard error when it has hats. It's a standard deviation when it does not have hats. This entire amount that you're adding and subtracting, this is your margin of error. I affectionately call this thing the MO. So putting this all together, you have the center plus or minus, everything after that is the MO. So looking at some examples of this, suppose that I go to Gallup poll and I look up the unemployment and I see that there is a 6% unemployment rate. With a margin of error of 3%. What's kind of neat is if I'm really good with the vocab, I can actually discover new things. So for example, I'm going to figure out how many people they asked in this poll. Here's how I'm going to do that. 6%, this is the estimate that they're giving me for the population. So my best point estimate, they're giving me my p hat. So p hat is 0.06. If 6% are unemployed, then that tells me my q hat, the remainder 94%, are employed. They wanted to be 95% confident. I'm getting pretty good at that one. To be 95% sure, I'm 2 standard deviations away. And finally, and most importantly, they say my MO is 3%. My formula for the margin of error is z star times the square root of p hat q hat all over the n. I'm going to plug in the values. My MO is 3%, so that's 0.03. I want to be 95% sure, so my critical value is 2. My p hat is 0.06. My q hat is 0.94. My number of samples, I don't know that. I'm calling that n. I don't have a ton of space here. I'm going to describe the steps, and I'm going to ask you to do them on your own to verify that the math works out here. But I'm trying to get this n by itself, so when I'm solving, I think opposites. To get rid of this multiplication, I'm going to divide this 2 over. To get rid of this square root, I'm going to square. When I square a fraction, I square both the top and the bottom. When I have a fraction equaling a fraction, my strategy is to cross multiply. So I'll end up with the n on this side. I'll end up with the 2 squared on this side. And I'll end up with this 0.03 squared over here still. So I've multiplied across, n ends up here, 2 squared or 4 ends up here. And finally, to get rid of this multiplication, I'm going to divide by that 0.03 squared. I'm going to type this into a calculator and see what I get. I got 250.6. They probably didn't ask 0.6 of a person. That'd be rude to start a question like, hey, are you, and then walk away. So let's assume that they asked 251 individuals at a minimum. Does that surprise you? Does that seem like a small number or a large number? I find that I have different emotional reactions kind of depending on the situation. So maybe you see this number and you think, I really wish they would have asked more people to try to figure out what's going on in the nation. I'm not sure if 251 is going to be representative. Or maybe you're thinking 251 seems pretty large. Usually when I do samples, I only ask 10 people. It will vary from problem to problem. Bit more vocab. What was Z star in this estimate? What was the best point estimate in the previous problem? A reminder, best point estimate is just the center. My center was a 6% success rate. So I'm guessing that 6% of those 251 people that they sampled were unemployed. Now I run into a little bit of an issue. If I wanted to be 90% sure instead of 95% sure, I'm going to have to change that Z star. Here's the process for doing that. I have it written in this paragraph below here. First step, I'm going to put C in the center of my curve. So boom, I put 90% in the center. If you'll recall, your normal table is shaded to the left. So my goal here is to find this Z-score for this little tail that's shaded to the left. C is always in the center because it's always part of this plus or minus part of the confidence interval. To find the Z star, I always have to rephrase this as the area to the left. Your table is shaded to the left. So if I have 90% in the center, then the area in both tails, and I'm going to call this alpha. I hope I don't use alpha for anything else important in the term, is 10% remaining. So if I just want one tail, left tail, I'm going to split this in half. Half of 10% is 0.05 or 5% sitting in this tail here. I'm going to look that up in my normal table. Now, when I look at this up in the normal table, I'm going to do it a little bit different than typical. So I'm not going to go 0.05 on the outside because this is not the Z-score. I'm going to have 0.05 on the inside. We're being joined here by Fiona in the corner. Hi, Fiona. So I'm finding 0.05. I have that here. Actually have that here and here. Do you see how 0.0505 and 0.0495 are both really, really close to 5%? I would say 5% falls halfway between these two values. Let's see what the Z-scores are for these by going out. So that's negative 1.6, that's how my Z-score starts. 4, that's how my Z-score ends. So my Z-score is somewhere between negative 1.64, this is the same thing but with a different last digit, negative 1.65 or so. Splitting the difference, I might say that my Z-score is negative 1.645. Now, Z star is a distance statement. I don't say stuff like I'm negative 1.645 miles away. So as a final step, I make Z star positive. I am 1.645 standard deviations away. So my Z score for this mark would be negative 1.645. And for this other mark, that would be the one if I was adding, that's a positive 1.645. So if you wanted to be 90% sure, you can add and subtract 1.645 standard deviations. I would ask you to go through these steps, but if you wanted to be 95% sure, That's about 2 standard deviations, or if you use the table to be a little bit more accurate, let's think through this process together. I have 95 in the center. 95 in the center leaves me with 2.5% for this little tail to the left. I'm going to go inside of my table and I'm going to find 0.025 and I'm going to see how close I can get. 0.025 happens here. That happens at negative 1.96. So my z-score, even more accurate than 2, it's actually 1.96 standard deviations away. I'll allow you to use either one of these critical values when you're working with 95%. I think 2 is easier when you're trying to do some math on the fly, but 1.96 is going to be more accurate. Finally, for 99%, I'm going to leave this one entirely for you to do, but I get a critical value of 2.576. We've now covered the equivalent of 2 or 3 lessons from a Math 243 class. It's a lot of stuff to go through, and it's still not everything that you probably need to review to get ready for the start of the term here, but I'm hoping it gives you somewhat of a foundation. That's going to be it for this first video, but I look forward to doing more with you in the future here.